do you think there's going to still be a role for things like simulation, human-driven test and measurement, given that AI is starting to be applied more and more in electronics and in particular in EMC?
Having played with AI and been deeply embedded in it for 2 or 3 years now, you can see where it's weak, and the weaknesses that it has lead me to believe that there's virtually no chance that it's going to get to a fully generative AI solution anytime soon.
Hello, everyone, and welcome to the Altium OnTrack Podcast. I'm your host, Zach Peterson. Today we're talking with Andy Eadie, owner of EMC FastPass and founder of Engentica. Andy Eadie provides EMC training through EMC FastPass, and he is developing a new platform called Engentica, and I'm very happy to be talking with him today. Andy, thank you so much for being here.
Thanks for having me. Really appreciate it.
So I got in touch with you because like some of the other innovators out there these days, I saw you were posting some cool stuff about what you're building on LinkedIn, and I knew I got to talk to this guy. So here we are today. Since you're a new guest on the show, if you could, just give us a brief intro to who you are and your background and how you got into electronics.
Yeah, sure thing. So I grew up in Scotland. My dad was an electrical engineer. He was actually in avionics in the Air Force. So from a young age, I was exposed to electronics. The garage was always full of things to tinker with and circuit boards. So I kind of followed that passion, and I went to Glasgow University, took electronics and electrical engineering there, and was there for 4 years, joined industry. I spent about 10 years as a hardware design engineer, initially working for a startup in Scotland, developing CD players. This was back around the year 2000. So it was kind of we were working on like a Sony mini disc competitor, which was a big technical challenge, but I learned a lot about control theory and analog electronics, and got to spend some time out in China at the manufacturing plant. So it was a good start to my career. And then I worked for Panasonic as a senior hardware engineer, working in consumer audio and FPGA design as well. So got some great experience with launching products and EMC and just learning a whole lot more. Fast forward, I opened an EMC Test Lab back in 2010. Here I moved to Vancouver Island, so that's where I am now. And I opened just a small independent EMC test lab with an open area test site. And I was doing CE mark testing and wireless certifications and things like that. And I got to work kind of hand in hand with a lot of design engineers, both testing the products and helping them to pass when they would inevitably fail. So I got pretty good visibility on the hardware side, and then learned a lot about the EMC testing side as well.
Now, we've had quite a few EMC consultants on the podcast, especially, I think, quite a bit more recently. And your story is kind of typical. Most people don't pick EMC as a career, but I think over time they see like a business opportunity, or they realize, hey, this is just really interesting. They didn't teach it in college, but it's important and interesting, so I want to get into it. What was it for you? Did you just see the business opportunity, and that's why you started a test lab?
A little bit of both, I would say. So I was fascinated with magnets as a kid. So, the iron filings experiment, bar magnet, you throw down some iron filings and you can see the magnetic field lines, and that just seemed like magic to me. But probably similar to other consultants, you just as the hardware design engineer, eventually it becomes your job to go to the lab and make it pass. And so once you're in, you're the guy once that happens. But then also on the business side of things, yes, it became apparent that there's a good little hardware design community here on Vancouver Island, and there was no test lab at the time. So I thought, hey, let's build it and serve that local community. And so, for the most part, it was Victoria companies, some from Vancouver, some from further afield. But I think it was a combination of interest and the business side of things, but also, from the test lab onwards, kind of seeing how difficult it was for companies to get through it, and how much of a kind of universal issue it is for most companies. Like then it sort of changed for me to think about how we can solve this on a kind of larger scale, to avoid a lot of the same issues coming up that keep happening. I think the average pass rate is worse than 50%. So it's an ongoing and a large issue. And I think once you're in the EMC industry, there's no shortage of work. So, it's a good industry to be in.
Yeah, there's definitely not a shortage of work, especially if you think about the recent FCC vote to ban testing of radio equipment from China.
That's going to be huge.
Yeah.
Huge.
Yeah, I think the future is looking pretty bright for U.S. and European EMC consultants and test labs.
Well, test labs, I think, are going to be, that's a really interesting to see what's going to happen there, because you can't build a lab overnight, right? Chamber manufacturers are on like a 8 to 10, sometimes 12-month lead time. So building that capacity elsewhere is going to be a crazy challenge. And I think about 2/3 of the test capacity is in China right now. So that's massive.
Also, probably a lot of EMC consulting opportunities, and especially training. And I think that's probably a good segue into what you do at EMC FastPass, which is providing EMC training.
Yeah. So after running the lab for a few years, and gaining that expertise. So back in 2015, I started producing online courses about EMC, both on the testing side of things and the design side, so circuit board design for compliance. And back then there was essentially no online courses for that. Of course, now there's a lot of offerings online. But ultimately, that was about trying to find a scalable solution for proliferating EMC knowledge. So that's kind of how EMC FastPass started. But yeah, I tried as much as possible to bridge the gap of hardware design, but also working one-on-one with the engineers trying to get their product through testing. I got to see the types of issues that would come up, and the patterns and the commonalities between failures. So that's what I tried to weave into online training. And so, since starting EMC FastPass around 2015, I've developed about 50 hours of training material that's available online to sign up at any time. And that's been rolled out to hundreds of companies now, from small startups to test lab staff to multinationals that are trying to train up teams on EMC. So that's been the bulk of the business since 2015.
Very, very cool. And I think definitely necessary, especially as the demographics of our industry, at least in the US and I think in Canada and Europe, tend to indicate, which is that you have probably in some areas of these regions a lot more retirements than people coming into the industry, and that's going to create a headache really for everybody, whether it's design or EMC or signal integrity or manufacturing. So I think a lot of new designers are going to start looking at this area as a potential career opportunity.
Yeah. And I do think it's worthwhile getting into. It takes, the loss of the senior engineers that have spent a career learn and burn, or burn and learn. It takes a lot of years to build up intuition, and the younger engineers, it does take take time to build that up, but that's what training's for, and learning.
A great question related to this that I like to ask all the EMC consultants that come in here is, what are some of the major misconceptions you've seen from new designers about EMC?
So one of the big ones I would say is that I noticed a general feeling of a lot of manufacturers is that it's not feasible to solve first time. So a lot of manufacturers just prepare up front that they're going to do 1 or 2 respins related to EMC, and they'll just budget for that, and they'll put time aside for that. And I don't think that's the case. That's not the way I operate. And I think that conceptually, if you think about, if you got to put together a dream team of EMC experts to develop a product, and in fact, some EMC experts do say, we guarantee that this will pass if I'm involved with the design of this product. So, they're thinking along the lines of, what do I need to do up front? What do I need to avoid? And they're thinking in terms of every design decision, they're thinking from their intuition of like, here's what we need to do and here's what we need to avoid. So yeah, I think that's a misconception. I think you can solve it up front. And actually, IBM came out with one of the first EMC rule checkers called EMSAT, I believe, back in the 90s. And when they were with their motherboard development, they actually published some stuff about this, and they were typically failing 1 or 2. They would do 1 or 2 respins per motherboard, specifically for EMC. So they built this software, and it's essentially a PCB layout checker, and it's running maybe 8 or 10 specific DRC rules, quite simple ones, and they managed to get their respins from 1 or 2 down to 0 on average. So they did manage to do that and address the problem up front. So that was just simple things like decoupling checks, like they set a minimum density of decoupling for grid squares, and they were looking at decoupling cap implementation, like minimizing inductance of vias to planes, things like that, diff pair quality and component placement. But it was all simple things that if you missed them, then you could definitely fail. But if you catch them, then you're going to save yourself a whole ton of time and money. So I think that's one of the biggest misconceptions.
Yeah, you mentioned planning for 1 or 2 respins. That mentality of we're going to fail, I think I have seen led to some interesting design decisions. I don't know why it's the aerospace guys, but I keep encountering from some aerospace companies that they will basically do things like split planes, just whatever they want in the stack up. Interesting things with switching regulators and power converters. And they basically say, yeah, we know it's probably going to fail, but I think it needs to be done like this. So we're not going to try and do it better up front.
Right.
Which is really weird. It kind of creates this, inevitable feedback loop of, we're just going to have to do the respins anyways. So I might as well not put in the effort now.
For hardware, that loop is so long, right? It's making the schematics, finalizing, it's producing the hardware, it's assembling, it's booking time at that test lab, which could be, a long lead time. So unfortunately, there's a lot of bad advice in application notes that leads to things like split grounds and all that stuff. But yeah, it's best to do it right up front, I think.
Yeah, I think for a company that's very large, like, let's say the Boeings of the world, right? They probably have their own test facilities and dedicated staff. But, once you go a little farther down the size spectrum for these companies, the time factor becomes even more important.
Yes. Yeah, 100%. And even the large companies with big labs, I've seen those backed up quite a bit as well. So they'll have multiple design sites and they're all funneled to one chamber asset or multiple, and they're backed up. So so if you can save, if actually for a mill standard company I was talking with a few weeks ago, they were saying each module that they develop is a 2-week schedule for testing. So that's a full suite of tests. And so if you fail, that goes back to the design guys, then back to the lab. So that's another 2 weeks. So they were properly backed up. But it's best to avoid that if you can, and why not, right?
Something else related to this is what are some of the challenges that you've seen when newer designers put their first designs or their first products through EMC testing, or maybe not even through formal testing, maybe just through pre-compliance?
So I think the biggest thing, if you're thrown in at the deep end as a new designer, you kind of just don't know what to expect. Often they don't know what the tests are even. So what is radiated emissions? What is conducted emissions? What are the suite of immunity tests that might be thrown at your product? So often they don't have that mental model of what their product is even going to be exposed to. So that's a major issue, because it's essentially a design requirement, right? It's your product has to meet these requirements. So if you don't know what those are, you can't work back to what you need to do in the circuit board or the enclosure. So that's a real challenge. The other big one is that the feedback loop is so slow. So if you're new and you're working on your first product or your first couple of products, you've spent all your time making the product, and then it's functionally working, but then it's your job to take it to the lab. And maybe you only get this opportunity once a year or twice a year if you're lucky. So you only have that time to learn for a very short period. And then, you got to go back to your office and figure out what was wrong, maybe buy test equipment. So I always say that I think hardware engineers have it a lot harder than software guys, because they just get to hit compile, and if there's an error, they're like, okay, I got to fix this line. So it's an instantaneous feedback, but for hardware engineers, it's months and months to get one opportunity for learning about EMC. So that's a massive problem.
Yeah, that's funny that you bring up the software guys, because I've worked with startups, and quite a few of the folks who run those companies have come from software, and then they have a really great idea, but they realize they need a custom PCB, and usually they start looking at Raspberry Pi and that kind of stuff, but they ultimately find I need something totally custom to create the desired user experience, and they start to learn that one through a really vicious cycle, that there is no just compile button and the hardware just magically updates, right? They have to actually rebuild a physical thing. And I mean, at minimum there's rework, but then they realize, oh, I don't even know how to do rework. Can you do that, Zach? Or, can you do that, Andy? Right?
Yeah. And then it gets real expensive real quick.
Exactly.
Yeah. So it's a real challenge. It takes years and years, I think, to build up that intuition. And I think for the newer engineers, even once they get their product back to their office, and say they have a test report that says they failed, they don't get instructions for how to fix it. It's just like, you failed and here you go. So at that point, the newer engineers need to know what levers are available to say, okay, how do I impact the performance of this test that I failed? And I like Ken Wyatt's approach to it. I think he calls it kill it dead, which is you throw everything in the kitchen sink at this EMC issue and just try and get it passing, try and get it to, get the emission down or get the ESD thing passing. And maybe all those things that you've thrown at it are not manufacturable or within your budget constraints or whatever, but you need to know where those levers are in order to solve the problem. But once you've thrown everything at it, you can work back to a manufacturable solution. But for newer engineers, even knowing what's available, what levers to pull, that's essentially like you got to go dive into app notes or YouTube or find resources, and so it's a challenge. Just it's a full learning experience.
Yeah, you're the first person to bring up Ken Wyatt's view on this, because I've never heard someone say it to me that way. But I've definitely had companies that I've worked with that have said, we can't get past pre-compliance, or we already failed 1 or 2 rounds of EMC testing, and it's getting extremely expensive at this point. And that's what they do. They throw every single thing they can think of at the
Yeah,
design. They'll come up with a list of 7 or 8 things, and they're like, please just do everything on this list.
yeah,
And they're just kind of hoping that one of those things solves the EMC problem on accident.
yeah. And it's funny, the longer the issue persists, the longer it fails, the more things become permissible to the company. The more relaxed the design constraints become. So initially it'll be, we can't possibly put this filter in, or we can't possibly modify the enclosure. And then 2 months passes of having no sales, and suddenly a lot more solution options become viable. So I've seen that quite a few times.
Yeah, that's another factor too. Yeah, and then you start seeing things like enclosure level shielding and shielding cans everywhere on the board, and all of a sudden
Yeah.
your product cost just inflated by 20 or 30%.
Yeah, and if you're lucky, you're in an industry where you've got those kind of margins. But for a lot of, for instance, consumer electronics products, or you're selling into a larger product supplier and you've committed to a certain price point, then you can really be in trouble. Like I've seen products where it absolutely needs a filter, but there was literally no budget, and they'd committed to a massive volume of shipping at a certain budget. So then you're in massive deep water of these commitments, and you need certain mitigation component options to get past these tests. And what do you do? So as a consultant, you often walk into these situations where there's no solution that will meet their existing design criteria. So that's a real challenge. But as most EMC consultants say, the cheapest solution is to get it right at the circuit board design stage, and then you're not left with these much more expensive options towards the end of the design cycle.
Now, speaking of software folks and I guess getting into hardware, of course, with AI, and we're 23 minutes in now, just now mentioning AI, with all there's a lot of software people getting into AI for hardware design. And I think it's to varying levels of success, right? I think you've got software people who at one point were also hardware people, and they understand a little bit more what happens in the hardware process, and the job that a hardware engineer has to do. But I do see some tech bros out there who are just like, software is going to make you and I completely obsolete by 2030. And you and I are going to be doing physical labor, I guess, the rest of our lives until we hope to retire, or we'll all be living off UBI. But it's funny because, I think the truth is somewhere in between. And so I guess this gets to my question. Do you think there's going to still be a role for things like simulation, human-driven test and measurement, given that AI is starting to be applied more and more in electronics, and in particular in EMC?
Yeah, 100%. So having played with AI and been deeply embedded in it for 2 or 3 years now, you can see where it's weak, and the weaknesses that it has lead me to believe that there's virtually no chance that it's going to get to a fully generative AI solution anytime soon. Like there's, just ask for your circuit board and it's going to do it. I don't see that happening. I think simulation companies like ANSYS are already leveraging really good parts of AI, but machine learning. So they can use their existing software to train ML models that vastly accelerate their simulation tools. And I think simulation is super useful and actually essential in many applications like signal integrity and power integrity and antenna design. And even for larger systems like vehicles, aerospace, where you have like tens or hundreds of modules and lots of cabling, I don't think there's any way to avoid simulation. With design cycles that are in the order of years, you have to look ahead with simulation to see the effects of various design choices. But at the circuit board level, I think that we're just so far away from a tool that can do it for you that I don't think that's going to be a major issue. But I do think that software design is quite far ahead in terms of use of AI, and that's because the software engineers are kind of scratching their own itch. That they have a lot more domain expertise on what software engineers need. I also think the stack of tools is much simpler than hardware design. Software is a much simpler stack, so it's much more suited to the feedback mechanism required to tune AI models. So you don't get the same. They don't have the same ability in hardware to implement a design and kind of get the feedback to the AI model of this is correct or this isn't correct. So I think that's an inherent thing that is going to inhibit at least or prohibit the fully generative AI design of hardware. But let's say even if that did happen, I think there's something called Jevons Paradox, where the more efficient something gets, counterintuitively, the more you get of it. So with software, the risk or the feeling is that, oh my God, we're going to lose software engineers. But actually what's happening is the exact opposite, because now all of a sudden it's much easier to build software. So you get more of it, and all the software engineers I know are like just 24/7, get your head down, because you've got the tools now to accelerate what you were already doing. So if you're a hardware company and now a circuit board design that would take you 6 months now takes you 3 months, like do you develop less products, or maybe instead you develop twice as many products? So I think it's probably more of an opportunity than it is of a potential risk.
Yeah, I was also talking to someone at an AI company recently, and he had mentioned that the companies that he talks to that are developing hardware, he asked them basically that question: what would you do if you got 50% of your time back in a product development cycle? And they all said we would do more testing,
right?
Which is pretty interesting, right? So they would actually do more of the things that prevent loss of money to the company through respins,
right?
And that could be functional testing, could be more software improvement kind of testing, or in this case, since we're talking about EMC, it could be more pre-compliance testing, and maybe they actually cut out one of those respins.
Yeah, that's an interesting perspective for sure.
Well, speaking of AI, you are developing a platform called Engentica, and I alluded to this at the very beginning of our discussion. So if you could, tell us about this platform and what are the goals that you have for this platform?
Yeah, so this tool, so Engentica, it stands for Engineering Agentic, and ICA's like knowledge. So it's an attempt at integrating essentially knowledge, domain-specific knowledge into the hardware design workflow. And also expert review. So you could think of it as kind of integrating training plus design review into an existing CAD workflow. And so maybe if I give you a demo, it's easier to show you than explain potentially.
Yeah, let's go ahead and jump in. We always like to see some demos.
Okay, so what the tool does, this is a Windows desktop tool, and we allow users to ingest schematics and layout, a netlist, BOM files, data sheets, design guideline documents, and company requirements into a single semantic database. So it's kind of it's like an intelligence layer that sits above the CAD layer, and it when the design files are ingested, it automatically categorizes things like components and nets and interfaces and scans power distribution trees, things like connectors. It also scans the layout. So we have both schematic data and layout data. So this design's an open source design called OpenRex, designed by Robert Ferenek, who you probably know. But it's a fairly complex design, 10 layers. And so, in a normal CAD tool, this would just exist. These would be objects in the CAD tool. But with Engentica, you can do things like on the right hand side, we have the chat window. And so we can say things like, tell me about the design. And so what's happening here is that Engentica is reading that question, deciding what facts about the design to package up and send to a language model for interpretation. So it happens fairly quickly, right? The language model is not deciding what it wants from the design. We actually pre-scan everything and decide what to provide to the language model for explanation. So it has a really good idea of what the design is, the design intent, the context, and so you can ask some really deep probing questions about the design, and that enables a whole bunch of things like deep design rule checking. And our DRC rules are focused on compliance related things like EMC, SI, and PI. But yeah, it really adds some power to what you can do with your existing CAD data. And if you like, I can dive into some more demo.
Yeah, and for everyone that's out there listening on audio, make sure to head over to YouTube to see this demo. Here we have some Altium schematics pulled up, which, as Andy said, were created by Robert Ferenek, and now he's got the chat window open to interact with the design. So make sure to head over to Altium Academy on YouTube to watch this.
Okay, so to boil it down, Engentica does three things. It runs intelligent compliance-focused checks on schematic and layout in order to surface risks, initially EMC focused. But yeah, it's designed to surface risk areas in your design, both in the schematic and the layout. The second thing it does that's kind of innovative is that you can explore highlighted risk areas in natural language, so you can investigate findings. And the third thing is it enables is the scaling of hardware design expertise and company requirements across large organizations. And really, the overall goal of it is to be able to catch predictable design risks earlier in the design cycle and reduce respins, of course, but also to train up engineers a lot faster on domain expertise that either we provide in the tool or the company can provide inject their own domain expertise into the tool so that it's proliferated amongst their engineers. So just as an example, if we go to the PCB layout, so we've got a number of geometric checks for the PCB layout. So this one is a well-known cardinal sin for EMC, which is never route critical signals over gaps in adjacent reference planes. And so here we can see a number of issues, and all across the board it's highlighted every situation where there's a net crossing a split in an adjacent plane. And so that's not particularly new. I think a lot of CAD companies have that, but we can investigate those and see if we actually have to do anything about them, because often, or more often than not, there's a trade-off, and so we need to be able to understand what that trade-off is, whether we need to actually address it, what options do we have, or whether we can just ignore it, right? Because sometimes you don't actually need to do anything. So it's in this way we can kind of build intuition much faster on what needs to be changed and what doesn't. And so in this case, actually what's happened is that this is an asymmetric stripline layer. So all of these tracks that you see here are much more tightly coupled to a ground plane on the opposite side than they are to this split power plane. So in this case, this isn't actually an issue, and that's why they're listed as an advisory. They're not listed as a warning or an error. So you can actually talk through this particular issue with a language model, and the language model gets the full context of this signal, including the design rule issue and the geometry of the signal and the configuration, i.e. is it an asymmetric stripline or whatever, the frequency. So in the chat here, it's essentially summarizing the issue and giving you some suggested action items, and actually, because it's de-risked to advisory, the recommendation is, you don't need to do anything about this. But you could investigate further and say, would this DRC be a bigger issue if this was DDR6 interface data signal? And then you would expect a different response, because the frequency for DDR6 is much, much higher than that signal. So in which case you do need to care about both reference planes. So this is kind of we think of it as kind of like a decision support tool. So in the cases where engineers, want more context and support of trying to figure out if they need to actually make an engineering change or not, that's what this is designed to help with.
Interesting. So you mentioned that a company can bring in, for example, like their own, I guess you could call it their own tribal knowledge, right?
Mm-hmm.
That could consist of a lot of things, right? Maybe it's, let's say, data sheets for proprietary components or modules, right? They're not sold on the open market, but the company has them and uses them. I could also imagine things like material test reports or component test reports for certain groups of components, their own internal, let's say, layout preferences, things like this.
Okay, so what we can do is we can inquire about a USB interface, and we actually have a skill pack an expertise pack that is all about how you deal with USB interfaces from an EMC perspective. So if I ask, analyze this USB interface from an EMC perspective, what's happening now is that Engentica is creating a package of information, including the connectivity, the layout data, and the expertise about USB interfaces. And it provides that to the language model for interpretation. And so the response that we get back is a synthesis of all of that data. And essentially what it's doing is it's reviewing the USB interface in the way that you encode into the expertise pack. So the types of data that's coming back is it's looking for common mode filtering, which we have here. And we're looking for ESD protection diodes, which are here. And we're looking for V-bus filtering. And so these are all guidelines and requirements that are in the expertise pack, and I'll show you in a minute what those look like. But you can also see scoring and statistics for the differential pair routing, which is very useful for figuring out if you're meeting the 90 ohm characteristic impedance target for USB 2. So it's essentially a full report on this USB interface, and a lot of it is based on this particular expertise pack, which is a concise guide about how you want to deal with USB 2 interfaces. And this is actually distilled down from 2 app notes created by Worth Electronic. They're really good app notes with case study information, actual design data, and parts recommendations for specific types of TVS diodes that you would want to use specifically for USB 2. So you could even ask, suggest a TVS diode for use with this USB 2 interface. Because we have that information encoded in the expertise packs, this should return specific part numbers that we could use here.
Yeah, I see a whole list of stuff here. Oh, I see. And then you went to the next part of the chat where you're requesting part numbers. I see. Okay. Yeah, now it's starting to return the part numbers now. Okay, very cool. So, I kind of see this immediately as very useful as like a design co-pilot, but where you can actually integrate custom knowledge. And I think that's one of the big pain points with some of the tools that are out there is how do you integrate any custom knowledge? And really, I don't see a way to do that. But here, you've basically done that as built into the system.
Yeah. I think language models, if you threw your design data at, say, ChatGPT or Claude, you get something back that sounds plausible, but could be nonsense. So
it's very confident nonsense, and sometimes
confident nonsense, and that's a result of they've trained it on the massive corpus of information on the internet. But of course, there's a lot of false or out of date information on the internet. Just as an example, decoupling. There's a ton of application notes that suggest use a 1 nanofarad, 10 nanofarad, 100 nanofarad cap for every power pin. And of course, now we know that can have unintended consequences like anti-resonances. So by using this approach of codifying the way you want to deal with things in your company, or you could just rely on our built-in core packs here. You get to kind of keep the language model on the rails and say, yes, you know what a decoupling capacitor is, but here's how we deal with it. So we want to standardize everything to 100 nanofarad cap of this particular part number, or here's how we deal with ESD protection in our company. So it's kind of a way to, both to kind of supercharge the knowledge that the language model has, because you can also add proprietary knowledge that isn't available on the internet, but also to keep it on the rails of, here's what's technically correct, here's the guideline that we want to follow. So that's how we're approaching it, and through our testing, it's giving really good results.
Well, I would encourage anyone that's interested in connecting with you, learning more about this, to go ahead and take a look at the links in the video description, and there will be some resources there where folks can learn more. We're getting up here on our time allotment, but what I would love to hear from you is, what do you see as coming up next on the roadmap for this platform?
So right now we're engaging with enterprises because I think this is the highest value that we can deliver right now. So right now, this is an early stage product. We're alpha build, so we're building out the robustness. We're testing the ingestion pipeline against a lot more Altium designs and just making sure everything's robust. But yeah, so we're getting involved with enterprise. We're doing co-development partnerships with a handful of enterprises. We've got a couple already, but we've got room for perhaps another 3 more. So if anyone's listening who's in a large company and you want to test this out at your company, if you have a lot of domain expertise that's siloed in a few people's heads and you want to proliferate that out across your hardware engineers globally, we definitely want to talk with you. But yeah, the kind of roadmap for this is going towards like a full EMC solution of catching these issues before any hardware is manufactured, but also we're going towards a fully interactive EMC troubleshooting tool. We see a lot of value there because, often it's too late and folks want solutions. So we're moving towards ingesting your design and being able to talk about risk areas and your issue in the full context of your design, and to be able to offer advice from a language model to help you to solve your EMC issues. So that's kind of where we're going.
Well, hopefully in the future, we also have the Engentica panel inside of Altium Designer, so folks can interact directly with all their design objects without leaving the tool. So as all of this stuff rolls out, of course, we'd love to have you come back on and discuss it. And as I said earlier, I hope folks who are interested will reach out and get a hold of you and learn more.
Really appreciate it. Thanks for having me.
To everyone that's out there listening and watching, we've been talking with Andy Eadie, owner of EMC FastPass and founder of Engentica. If you're watching on YouTube, make sure to hit the like button, hit the subscribe button. You'll be able to keep up with all of our podcast episodes and tutorials as they come out. And last but not least, don't stop learning, stay on track, and we'll see you next time. Thanks, everybody.